At the next intersection, turn right. At the next intersection,
Hello everyone and welcome to another video on our own devices. I'm Jean Messier, and today we're having a look at a fascinating trio of nautical navigation instruments. Now, I know what some of you are thinking right now. Geez, why don't you just rename the channel Gilles' Wonderful World of Navigational Instruments and Vintage Cameras? And, well, what can I say? Those types of devices really hit the sweet spot for me when it comes to clever mechanical solutions to complicated problems. Anyway, the instruments here, at least one of them, were brought to my attention by viewer Tony Funtek, and while doing some research to answer some of his questions, decided to get my hands on them and feature them on this video. So what I have here are a Pelorus board, a course corrector, and a marine computer. And so let's have a look at these one at a time. Right, so the first instrument I have here is called a Pelorus or Pelorus, depending on where you come from. I've heard it both ways, so I'm going to stick with Pelorus. So this is named after a pilot or navigator who served under Carthaginian general Hannibal Barca during the 3rd century BCE, and is also sometimes known as an alidade or a maneuvering board. Now, this particular model was manufactured by James Bliss and Company Incorporated of Boston, Massachusetts, and is copyrighted 1956. And as you can see, is laid out with a regular compass rose, though there is no directive element, that is, no magnetic compass needle or gyro compass repeater. This is because the Pelorus is used to measure bearings relative to your ship's current course. So, for example, you can use a Pelorus to measure the bearing to a celestial object, such as a star or a planet, and thus verify your intended course and correct for any errors produced by other navigational instruments. If you're operating near the shore, you can take sightings of land features to make sure that you are maintaining your course and a safe distance from the shore. And if you're traveling in a convoy or other group of vessels, you can take multiple sightings of another vessel to make sure it is maintaining a constant course and thus avoid collision. So there's all sorts of different things you can use this for. Now, Peloruses, and yes, that is the proper pluralization, come in all sorts of shapes and sizes. On larger vessels, the Pelorus will typically be mounted on a pedestal near the main compass binnacle or gyro compass repeater. It will often be fitted with gimbals or even a gyroscope to keep it level, and with a telescope rather than simple sighting vanes in order to make more accurate sightings. Though for smaller vessels, portable Pelorus boards like this one are also sold. And these can be used pretty much anywhere on a vessel, though to function properly, you need to align one of these two lubbers lines with the longitudinal axis of the ship and rotate the compass card to match the ship's compass. You can then make a sighting using this rotating arm with its two sighting vanes. Now, an alternative to having a separate Pelorus is to fit the main compass binnacle or gyro compass repeater with something called an azimuth circle or azimuth mirror. And in the latter case, this will have a system of mirrors or prisms that allow you to view both the compass needle and the object that you are sighting at the same time. Otherwise, the standard procedure is for the helmsman to call out the compass bearings to the navigator while they are using the separate Pelorus. So the next instrument we're going to have a look at was manufactured by the Marine Dynamics Company of Flushing, New York, and is copyrighted 1961. This is actually two instruments in one, mounted on both sides of this plastic disc. And the first one we're going to have a look at is this course corrector. So this is actually the instrument that was brought to my attention by Tony, although his example was a much nicer version made of metal and wood dating from the Second World War. And what this allows you to do is convert between your compass course and your true course and to calculate compass error. Now, there are two types of error which will cause your compass course, the bearing given by your magnetic compass needle, and your true course, your actual bearing relative to the Earth's surface, to differ from one another. And these are magnetic variation and magnetic deviation. Now, magnetic variation or declination results from the fact that the magnetic and geographic poles are not aligned with one another. Indeed, as of this recording, the North Magnetic Pole lies around 500 kilometers or 312 miles from the North Geographic Pole, though this is an estimate because the actual position of the magnetic pole was last measured in 2007, and this position has been constantly drifting across the Arctic Ocean towards Siberia by around 55 kilometers or 34 miles every year. So the value of magnetic variation or declination varies depending on your position on the Earth's surface, getting progressively larger as you near the poles. And indeed, when you're operating near the magnetic poles, magnetic compasses become all but useless, and you have to use other navigational instruments such as gyrocompasses or astrocompasses. And I've actually covered astrocompasses in a previous video. So if you want to learn more about that, please check out the link in the description. Now, navigators will have access to tables or charts showing the value of magnetic declination for every point on the Earth's surface. And these charts will typically feature something called isogonic lines, which are like the contour lines on a topographical map, only instead of denoting lines of equal elevation, they denote lines of equal declination. The Earth also has what's known as an agonic line running around both poles, along which there is zero declination because the magnetic and geographic poles are aligned, though this line is not perfectly straight because the Earth's magnetic field is not perfectly symmetrical. Now, the second type of compass error is what's known as magnetic deviation, and this results from magnetic interference from a ship's metal hull. Now, some of you might have noticed on older ships that the compass binnacle is often flanked by a pair of large iron balls, typically painted green and red to indicate the starboard and port sides of the ship. So these are known as Kelvin's balls or navigator's balls, giggity, and are used to compensate for the magnetic interference of the ship's hull. Yet even with such compensation installed, there will still be a certain amount of error imparted by the ship's hull. And the value of this error actually changes depending on your compass heading, because the magnetic lines of force will be distorted differently depending on what angle they cut through the hull. And so every ship will have a table unique to that ship listing the value of magnetic deviation for each compass heading. Now, as I mentioned earlier, the bearing given by your magnetic compass needle is known as your compass course. Now, if you correct your compass course for magnetic deviation, then you end up with your magnetic course. And if you then correct your magnetic course for magnetic variation or declination, you get your true course. And that is what this course corrector is designed to help you calculate. So as you can see, we have an outer scale giving our true course, an inner scale giving our magnetic course, and then two movable disks allowing us to enter our magnetic deviation and variation, and a rotating cursor to allow you to read the output. Right, so as an example, let's say we were traveling along a compass course of 35 degrees. We know that our magnetic deviation is 4 degrees east and that our magnetic variation or declination is 9 degrees west. So using the two movable disks, we would enter our deviation and variation, following the rule that errors east are added to the bearing and errors west are subtracted from the bearing, since compass bearings are read clockwise around the compass rose from north. Then we swing our cursor around to align with 35 degrees magnetic course and find that our true course is 30 degrees. Now you can also use this in reverse to determine your magnetic course from your true course, and navigation schools will often teach students a simple mnemonic to help them remember how to apply errors. And this is called the cadet method. So looking at the word cadet, you can see that if we go from our compass course to our true course, you add east error. And then if you want to go from your true course to your compass course, you do the reverse. And finally, you can use this to calculate your compass error. So for example, if we know our true course using something like a gyrocompass, we know our magnetic course from our magnetic compass, and we know our magnetic deviation from the chart that is unique to the ship we are sailing in, then you can enter all of those values here and figure out what your magnetic variation or declination is on that point of the Earth's surface. Now, something worth pointing out here is that these are very simple calculations that could easily be done by hand using pencil and paper. However, if, as a navigator, you have to do a lot of these calculations in a row, it is still handy to have a simple circular slide rule like this in order to reduce the amount of small calculation errors that creep into your work, since small mathematical errors early on can lead to huge navigational errors when traveling long distances. Anyway, let's move on to the other side of this disk where we have a marine computer. And this is also a relatively simple device that does relatively simple arithmetic, but is still very handy to have when doing real-world navigation in order to reduce errors. And in this case, what this allows you to do is convert between time elapsed, distance covered, and speed. So on the outer dial, we have our distance in miles on one side and speed in knots on the other. Now on the inner dial, we have our elapsed time in minutes on one side and hours on the other, and 3 indicator arrows, 1 for speed in knots and 2 for distance in statute and nautical miles, offset from one another because a nautical mile is 1.508 times longer than a statute mile. So the instruction booklet for this computer gives a number of examples of the types of calculations you can perform. So for example, if a distance of 0.8 of a mile is covered in 9 minutes and 30 seconds, to find our speed in knots, we align 9.5 minutes on the inner dial with 0.8 miles on the outer dial, then look at the speed pointer and see that it is pointing at 5.05 knots. If instead you measure your speed as 5.05 knots and sail for 2.5 hours, you can find the distance covered by aligning the speed pointer on the inner dial with 5.05 knots, then look across the 2.5 hour mark to find a distance of slightly more than 12.5 nautical miles. Finally, if your speed is 12 knots and you need to cover a distance of 33 miles, you can find the elapsed time by setting the speed pointer to 12 knots and reading opposite 33 on the outer dial to find a time of 2 hours and 45 minutes. Anyway, that's all I have for you today. Thank you so much for watching, and a huge shout out to Tony for bringing these instruments to my attention. If any of you out there have suggestions for video topics or even objects themselves gathering dust on a shelf somewhere that you would like to send in to me for me to cover in a video, please let me know at the email address below. Anyway, I'll see you next time on another video where we'll look at yet more fascinating navigational instruments and other devices just like these. Until then, I'm Jean Messier from Our Own Devices. Have a great day.